Hello, friend. If you're here, it means you're looking for something quiet, something that makes sense of the noise. Tonight, we're going to talk about forces, not the kind that push you around, but the kind that hold everything together, the kind that keep atoms from flying apart, stars from collapsing, and you from floating away into nothing. Some nights, when you look up at the sky, you might wonder why anything exists at all. Why doesn't the universe just scatter? Why do things stay? Why does the moon circle the earth, your heartbeat in rhythm light, travel in straight lines until it bends? The answer is simpler than you think and stranger than you'd believe. 4 forces. Just 4. That's all it takes to hold the cosmos together. Before we begin our quiet journey through the invisible architecture of reality, if you find comfort in these stories, told softly, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more science whispered into the dark, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Tonight, we'll walk through the forces that shape everything. Gravity, which bends space itself. Electromagnetism, which lights up the world. The strong nuclear force which binds atoms so tightly they can power stars. And the weak nuclear force, which lets things change, decay, transform into something new. You don't need equations. You don't need to remember names. Just rest and let curiosity do the listening. Scientists spent centuries trying to understand why things fall, why magnets stick, why the sun burns without consuming itself. Isaac Newton thought gravity was a force that pulled. Albert Einstein said, "No gravity isn't a pull. It's a curve in the fabric of space and time itself." Then, quantum physicists discovered forces so small, so strange, they operate in realms where reality itself seems to flicker and fade. But here's what they all found. Everything in the universe, from the smallest quark to the largest galaxy, is held together by just 4 fundamental forces. Not 5, not 100. 4. And the strange part, they're not equal. Gravity is the weakest, by far. A tiny refrigerator magnet can lift a paperclip off a table, overcoming the gravitational pull of the entire Earth beneath it. Yet, gravity shapes galaxies, bends light, and keeps planets in their orbits for billions of years. It's weak, but it reaches infinitely far. Electromagnetism is stronger, much stronger. It's the force that keeps your hand from passing through this screen, that makes lightning crack across the sky, that lets neurons fire in your brain so you can think these thoughts. Without it, atoms would never bond. Chemistry would never happen. You would never happen. Then there's the strong nuclear force, the most powerful of all. It operates only at distances smaller than an atom's nucleus, but within that tiny realm, it's 100 times stronger than electromagnetism. It's what keeps protons, which are all positively charged and should repel each other, locked together in every atom. Without it, matter itself would disintegrate. And finally, the weak nuclear force. It's responsible for radioactive decay, for certain nuclear reactions, for processes that let stars shine and elements transform. It's weak, yes, but without it, the sun would go dark. Carbon wouldn't exist. Life wouldn't exist. 4 forces, each with a role, each perfectly balanced. If gravity were just slightly stronger, say 1% more powerful, stars would burn through their fuel too quickly. They'd collapse, before life could ever begin. If electromagnetism were a little weaker, atoms wouldn't hold together. Water wouldn't exist. DNA couldn't form. Scientists have measured this balance. The numbers are absurd. Some of these forces are fine-tuned to 1 part in 10 to the 60th power. That's a 1 with 60 zeros after it. Imagine adjusting a dial with that many settings, and only one of them allows a universe where stars can form, atoms can bond, and beings can wonder why. This isn't philosophy. This is measurement. This is what physicists found when they looked closely at the fundamental constants of nature. Now you might think maybe there are other universes out there with different settings. Maybe we just happen to live in the one that works. And maybe that's true. But here, in this universe, in this moment, you exist because 4 forces are perfectly mysteriously balanced. The ancient Greeks thought everything was made of earth, water, air, and fire. They were wrong about the elements, but they were on to something. There are indeed 4 fundamental things that shape reality. We just didn't know what they were until much, much later. Newton published his law of universal gravitation in 1687. He described gravity, mathematically showed how it governed falling apples and orbiting moons with the same elegant equation. But he couldn't explain what gravity actually was. He called it action at a distance, objects pulling on each other across empty space with no medium, no connection, no reason. It bothered him. He wrote that he framed no hypotheses about the cause, only described the effect. It took over 200 years for Einstein to answer Newton's question. In 1915, Einstein published his theory of general relativity. He said, gravity isn't a force pulling objects together. It's the shape of space and time itself. Massive objects bend space-time the way a bowling ball bends a trampoline. Smaller objects roll toward the depression, not because they're being pulled, but because they're following the curved path. It sounds abstract, but scientists have tested it. In 2015, instruments called LIGO detected gravitational waves ripples in space-time itself, caused by 2 black holes colliding over 1 billion light-years away. The collision happened 1.3 billion years ago, and the ripples traveled across the universe, stretching and compressing space itself by less than the width of a proton, until finally, on September 14th, 2015, we felt them here on Earth. We didn't just see gravity, we heard it. The universe rang like a bell. Electromagnetism was unified in the 1860s by James Clerk Maxwell. Before him, electricity and magnetism seemed like separate phenomena. But Maxwell wrote 4 equations, just 4, that showed they were 2 aspects of the same force. Light itself, he realized, was an electromagnetic wave. Every color you've ever seen, every radio signal, every X-ray, every microwave, all electromagnetic radiation, just at different frequencies. His equations predicted that these waves travel at a specific speed about 300,000 kilometers per second. Scientists measured the speed of light. It matched. Maxwell had accidentally discovered what light was made of. The nuclear forces took longer. They operate at scales so small we couldn't detect them until we built machines powerful enough to smash atoms apart and see what was inside. In the 1930s, physicists discovered the strong nuclear force, though they didn't understand it yet. They noticed that atomic nuclei shouldn't exist. Protons are all positively charged, and like charges repel. Pack them together in a nucleus, and they should fly apart instantly. But they don't. Something holds them. That something is the strong force carried by particles called gluons, binding quarks together into protons and neutrons with a grip so fierce it takes enormous energy to break. The weak force was even stranger. In 1896, Henri Becquerel discovered that uranium emitted invisible rays. Marie Curie called it radioactivity. But what was happening? Why did some atoms decay while others stayed stable? Eventually, scientists realized the weak nuclear force allows particles to transform. A neutron becomes a proton, releasing an electron and a neutrino. This process powers the sun. It's why carbon dating works. It's why smoke detectors function. By the mid-20th century, physicists had identified all four forces. They'd measured them, described them mathematically, tested them in experiments. But one question remained. Why four? Why not one? Why not 3 or 7 or infinite forces, each governing a different aspect of reality? Einstein spent the last 30 years of his life trying to unify gravity and electromagnetism into a single framework. He failed. He died in 1955 without finding the answer. But others kept looking. In the 1960s and 70s, physicists unified electromagnetism and the weak force into something called the electro-weak interaction. At high enough energies, they're not separate. They're one force split into two in the cooler universe we live in now. That leaves 3: gravity, electro, weak, and strong. Scientists are still trying to unify them. String theory proposes that all particles are tiny, vibrating strings, and the different vibrations produce different forces. Loop quantum gravity suggests space-time itself is quantized, made of discrete units. Neither theory is proven yet. Maybe one day we'll find a single equation that describes all four forces. A theory of everything. Maybe not. But even now, with what we know, the picture is beautiful. Every thought you think is neurons firing electrically, electromagnetism. Every breath you take is molecules held together by electromagnetic bonds pulled into your lungs by air pressure, which is molecules colliding. Your body is made of atoms held together by a strong force built from elements forged in dying stars. And you stand on this planet because gravity bends space-time around Earth's mass, keeping you here, keeping the air here, keeping everything from drifting into the void. You are held together by forces you cannot see. And somehow, those forces are balanced so precisely that stars burn for billions of years, planets form, chemistry happens, and life, strange, fragile, wondering life, emerges to ask why we don't have the final answer yet. Maybe we never will. But we've mapped the invisible threads that weave reality together. 4 forces, infinite manifestations. Tonight, we'll explore each one. Not with equations, not with proofs, but with wonder. We'll see how they work, where they came from, what they do, and why, without them, nothing would exist. Starting with the weakest force of all, the one that bends everything. Gravity is the strangest force of all. It's everywhere. It holds planets in orbit, keeps galaxies from flying apart, bends the path of light itself. But here's the thing. It's weak. Unimaginably weak. So weak that right now, as you rest, the electromagnetic forces between the atoms in your body are overpowering the gravitational pull of the entire planet beneath you. Think about that. Every atom in the Earth, trillions upon trillions of them, pulling down on you with gravity. And yet, your muscles can lift your hand. Your heart can pump blood upward. A bird can fly. A single beat of a hummingbird's wings defeats the gravity of a planet. Gravity seems powerful because it adds up. One atom's pull is nothing. But collect enough atoms, say the mass of Earth, about 6 trillion kilograms, and suddenly, gravity shapes everything. Isaac Newton figured this out in the 1680s, though the famous story about the apple is probably exaggerated. What Newton realized was this: the same force that makes apples fall also keeps the moon in orbit. Gravity isn't something that only works down here. It's universal. He wrote an equation. Simple, elegant. The force between two objects depends on their masses and the distance between them. Double the distance, and gravity becomes 4 times weaker. Triple it, 9 times weaker. This is called the inverse square law, and it governs how gravity spreads through space. But Newton didn't know why. He described how gravity behaved, but he couldn't explain what it was. In his own words, he found it inconceivable that inanimate brute matter should, without the mediation of something else, operate upon and affect other matter without mutual contact. Something about gravity bothered him. It acted instantly across empty space with no medium, no delay, no mechanism. He called it action at a distance and admitted he had no explanation. For over 200 years, no one did. Then came Einstein. In 1915, Albert Einstein published his general theory of relativity, and everything changed. He said, "Gravity isn't a force, it's geometry. Mass doesn't pull on other mass. Mass bends space and time, and objects move along the curves. Imagine a trampoline stretched flat. Roll a marble across it and it travels in a straight line. Now place a bowling ball in the center. The trampoline sags. Roll the marble again, and it curves toward the depression. Not because the bowling ball is pulling it, but because the surface itself is curved. That's what Earth does to space-time. The sun does it on a larger scale. Black holes do it so extremely that not even light can escape the curve. Scientists have tested this. In 1919, during a solar eclipse, astronomers measured the positions of stars near the sun's edge. Light from those stars bent as it passed through the sun's gravitational field, shifting their apparent positions by exactly the amount Einstein predicted. Space itself was curved. It sounds abstract, but the effects are real. GPS satellites orbit Earth at about 20,000 kilometers up, where gravity is weaker. Time runs slightly faster there, about 45 microseconds per day faster than on the ground. If engineers didn't account for this, GPS coordinates would drift off by several kilometers within weeks. Your phone's map app works because we corrected for Einstein's equations. Gravity bends time. It bends space. And in 2015, scientists proved it could make waves. On September 14th, at 5:51 a.m. Eastern Time, 2 detectors in the United States, one in Louisiana, one in Washington State, felt space-time itself ripple. The signal lasted less than a second, but in that fraction of a second, scientists detected the collision of 2 black holes over 1 billion light-years away. The black holes had circled each other for millions of years, spiraling closer, moving faster, until finally they merged. The collision released more energy than all the stars in the observable universe combined for that brief instant. Not as light, as gravitational waves. Those waves traveled outward at the speed of light, stretching and squeezing space-time itself. By the time they reached Earth, they were faint, stretching space by less than 1,000th the width of a proton. But sensitive enough instruments called LIGO felt them. For the first time in history, we didn't just see the universe, we heard it. Gravity made a sound. Now here's something most people misunderstand. Astronauts floating in the International Space Station aren't weightless because there's no gravity up there. The ISS orbits at about 400 kilometers above Earth's surface. Gravity at that altitude is still about 90% as strong as it is on the ground. So why do astronauts float? Because they're falling. Constantly. The ISS is falling toward Earth at the same rate the astronauts inside are falling. They're in free fall together, so relative to each other, they appear weightless. If the station stopped moving, it would crash straight down. But because it's moving forward at about 28,000 kilometers per hour, it keeps missing the Earth falling around the curve of the planet instead of into it. That's what an orbit is. Falling sideways fast enough that you keep missing the ground. Here's another curious fact. Gravity doesn't just pull objects together. It also determines how time flows. The stronger the gravitational field, the slower time passes. Imagine two twins. One stays on Earth. The other travels to a black hole's edge, hovers there for a while, then returns. When they reunite, the traveler will have aged less. Not because of speed, though that also affects time, but because time itself runs slower in stronger gravity. This isn't science fiction. It's been measured. Atomic clocks placed at different altitudes tick at different rates. A clock at sea level runs slower than one on a mountaintop, even if the difference is only a few billionths of a second per day. Gravity and time are woven together. You can't separate them. Now let's talk about something strange. Most of the gravity in the universe doesn't come from things we can see. Astronomers have studied how galaxies rotate. Based on the visible matter, stars, gas-dust galaxies should fly apart. The outer stars are moving too fast. There isn't enough mass to hold them in orbit. Yet, they don't scatter. Something invisible is keeping them together. Scientists call it dark matter. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetism at all. The only way we know it exists is through its gravitational pull. And there's a lot of it. Current estimates suggest that about 85% of all matter in the universe is dark matter. We live in a cosmos where most of the mass is invisible, known only by the way it bends space and pulls on the things we can see. We don't know what it's made of. We've never detected a dark matter particle directly, but we see its effects everywhere, in the rotation of galaxies and the way light bends around galaxy clusters in the large-scale structure of the universe itself. It's as if the universe is held together by ghosts. Here's something else that puzzles scientists. Gravity doesn't fit with the other forces. Electromagnetism. The strong force and the weak force are all described by quantum mechanics. They operate through particle exchanges, through probabilities, through fields that fluctuate at the smallest scales. But gravity resists quantum description. Einstein's general relativity works beautifully at large scales. Planets, stars, galaxies. Quantum mechanics works beautifully at small scales, atoms, particles, fields, but try to combine them, and the math breaks down. At the smallest scales, distances around 10 to the power of minus 35 meters, called the Planck length, both theories should apply. But they give contradictory answers. We don't have a theory of quantum gravity yet. This is one of the biggest unsolved problems in physics. How do you unify the force that shapes galaxies with the rules that govern particles? Some scientists think the answer is string theory, where particles are tiny, vibrating strings, and gravity emerges from their vibrations. Others think space-time itself is made of discrete quantized units, a kind of pixelated reality at the smallest scales. Still, others think we're missing something fundamental, some deeper principle we haven't discovered yet. The question remains open, but even without a final theory, we've learned this gravity is patient. It's weak, yes, but it never stops. It never turns off. It reaches infinitely far, thinning with distance, but never vanishing. Given enough time, gravity always wins. It pulls gas clouds together until they collapse into stars. It gathers stars into galaxies. It clusters galaxies into superclusters, weaving the universe into a vast cosmic web of matter and void. And someday, trillions of years from now, gravity may pull everything back together, or it may lose to dark energy, and the universe will expand forever, stars growing dimmer and farther apart, until the last light fades, and only cold, silent darkness remains. We don't know which future awaits, but we know gravity will shape it. For now, here on Earth, gravity keeps you grounded. It keeps the air around you, the water in the oceans, the moon circling overhead. It keeps your blood flowing downward, your bones strong from resisting it, your sense of up and down intact. Without gravity, you'd drift. The atmosphere would escape into space. Earth would never have formed in the first place, just a cloud of dust scattered across the void. But gravity gathered that dust, pulled it together, compressed it until it heated, until it melted, until it formed a molten core and a solid crust and oceans and an atmosphere. And eventually, impossibly, you, the weakest force, the most patient, the one that bends everything, including time itself. But there's another force at work in your body right now, stronger and faster, holding atoms together, making chemistry possible, letting neurons fire so you can hear these words. That force doesn't bend space. It fills it. It lights it up. Every color you've ever seen is a lie. Not because colors don't exist, but because they're not out there in the world. They're in here, in your mind, interpreting electromagnetic waves. Red isn't red. It's light vibrating at about 430 trillion times per second. Blue is 670 trillion. Your brain translates frequencies into the experience of color. Everything you see is light. Everything you touch is electromagnetic force. Every thought firing in your brain right now is electricity dancing between neurons. This is the force that makes chemistry possible, that builds molecules, that holds your body together. Without electromagnetism, atoms would be just lonely nuclei floating in space, never bonding, never building, never creating the complexity that allows stars to burn flowers to bloom, or you to wonder about forces you cannot see. Electromagnetism isn't one force. It's two phenomena woven together so tightly that for most of history, humans didn't realize they were connected. Ancient Greeks knew about static electricity. Rub amber with fur, and it attracts small objects. They called amber electron. That's where the word comes from. Ancient Chinese knew about magnetism. Lodestone, a naturally magnetic rock, always points north. By the 11th century, they were using magnetic compasses for navigation. But electricity and magnetism seemed separate. Lightning was one thing. Magnets were another. No one suspected they were two faces of the same force. Then, in 1820, a Danish physicist named Hans Christian Ørsted was giving a lecture. He set up a demonstration with a compass and a wire. When he passed electric current through the wire, the compass needle moved. Not much, just a flicker. But it moved. The room went silent. Electricity could create magnetism. That meant they were connected somehow. Within weeks, other scientists jumped on the discovery. André-Marie Ampère in France developed mathematical descriptions. Michael Faraday in England discovered the reverse moving magnets could generate electricity. Spin a magnet near a coil of wire and current flows. This is how generators work. This is how power plants function. Move something magnetic. Get electricity. But the real breakthrough came in the 1860s from a Scottish physicist named James Clerk Maxwell. Maxwell was a theorist. He didn't do many experiments himself. Instead, he took all the scattered observations about electricity and magnetism and tried to unify them mathematically. He wrote 4 equations, just 4, that described how electric and magnetic fields interact, how they generate each other, how they propagate through space. And then he noticed something strange in his equations. If you disturb an electric field, it creates a magnetic field. That magnetic field changing creates another electric field, which creates another magnetic field, which creates another electric field. The disturbance propagates. A wave, electromagnetic wave. Maxwell calculated how fast this wave should travel. He got a number approximately 310,000 kilometers per second. That number was familiar. Scientists had measured the speed of light, about 300,000 kilometers per second. Maxwell realized light is an electromagnetic wave. Visible light, the stuff you see with your eyes, is just oscillating electric and magnetic fields rippling through space. It was one of the most beautiful insights in the history of science. Light wasn't some separate phenomenon. It was electromagnetism in motion. But there's more. Visible light is just a tiny sliver of the electromagnetic spectrum. Change the frequency, and you get radio waves. Increase it further infrared. More visible light. More ultraviolet. Keep going X-rays, gamma rays. It's all the same thing. Just different frequencies. Your microwave oven, your Wi-Fi router, your cell phone, the sun's warmth on your skin, the X-ray at the dentist, all electromagnetic radiation. The only difference is how fast the waves oscillate. Radio waves vibrate millions of times per second. Visible light, hundreds of trillions. Gamma rays, quintillions. Your eyes evolved to detect a specific range, the range where the sun emits most of its energy and where Earth's atmosphere is mostly transparent. Not coincidentally, this is also the range where water is transparent, which makes sense for creatures that evolved in and around water. But here's the thing. Most people don't realize you're not actually seeing objects. You're seeing light that bounced off objects. The book in your hand doesn't glow. It reflects light. Your brain interprets the reflected wavelengths as color, the patterns of light and shadow as shape. In total darkness, the book is still there. But you can't see it because there's no light to reflect. Even stranger, you're not actually touching the book. This sounds wrong. You can feel it in your hand. But what you're feeling isn't contact. It's electromagnetic repulsion. Atoms are mostly empty space. The nucleus is tiny. If an atom were the size of a football stadium, the nucleus would be a marble at the center. Electrons orbit far out in the stands. Everything in between is emptiness. When your hand approaches the book, the electrons in your hand's atoms get close to the electrons in the book's atoms. Electrons are negatively charged. Like charges repel. The electromagnetic force pushes back. You feel that push as solidity, as texture, as resistance. But the atoms never touch. There's always a gap, a tiny space, where electromagnetic fields are shoving against each other. You've never touched anything in your life. You've only ever felt repulsion. This is why you don't fall through the floor. The electrons in your feet repel the electrons in the ground. The floor feels solid because electromagnetic forces are incredibly strong at small distances. How strong? Compared to gravity, electromagnetism is about 10 to the 36th power times stronger. That's a 1 with 36 zeros. If you could somehow turn off electromagnetism between your body and Earth gravity alone would pull you down with a force so weak you could jump to the moon. But you can't turn it off. Electromagnetism is always on, always pushing, always pulling, holding molecules together, keeping solids solid, making liquids liquid, defining the boundaries between things. Every chemical bond is electromagnetic. When two hydrogen atoms bond with an oxygen atom to form water, it's because electrons are shared between them, held by electromagnetic attraction between negative electrons and positive nuclei. That's a covalent bond. When sodium and chlorine form table salt, sodium gives an electron to chlorine. Now sodium is positively charged. Chlorine, negatively charged. Opposites attract. That's an ionic bond. When metals conduct electricity, it's because some electrons are free to drift through the lattice of nuclei, creating a sea of mobile charge. That's a metallic bond. All chemistry, all molecular structure, all the complexity of life itself. It's electromagnetism arranging atoms into patterns. Your DNA is held together by electromagnetic forces. Hydrogen bonds between base pairs, adenine to thymine, guanine to cytosine. Weak enough to unzip when needed, strong enough to keep the code intact. Your muscles contract because calcium ions electrically charged trigger proteins to slide past each other. Electromagnetic attraction and repulsion coordinated across millions of molecules. Your neurons fire because sodium and potassium ions flow through channels and cell membranes, creating electrical signals that propagate down nerve fibers at up to 120 meters per second. Every thought, every memory, every sensation, electricity, and light. Light is how you perceive the world. Photons, particles of electromagnetic radiation, stream from the sun, bounce off surfaces, enter your eyes, strike cells in your retina trigger. Chemical reactions send electrical signals to your brain. But photons are strange. They have no mass. They always travel at the speed of light, exactly 299,792,458 meters per second in vacuum. Not approximately. Exactly. We define the meter based on how far light travels in a specific fraction of a second. And here's something curious. The speed of light isn't really about light. It's the speed of causality. It's the maximum speed at which information can travel through the universe. Light happens to move at that speed because photons have no mass. But the speed itself is a fundamental property of space-time. Nothing with mass can reach it. As you accelerate closer and closer to light speed, you need more and more energy. To actually reach it would require infinite energy. The universe won't allow it. But light itself, massless and swift, crosses the cosmos at that ultimate speed. The light reaching your eyes right now from the sun left the sun's surface about 8 minutes and 20 seconds ago. The sun could have vanished 8 minutes ago, and you wouldn't know yet. You'd still see it shining, still feel its warmth, until the last photons arrived. Light from the nearest star beyond the sun, Proxima Centauri, takes over 4 years to reach us. Look at it tonight, and you're seeing it as it was 4 years ago. Light from the Andromeda Galaxy takes 2.5 million years to arrive. The photons entering your eye left that galaxy before humans existed. Looking out into space is looking back in time. The deeper we observe, the older the light. The farthest light we've detected comes from 13.8 billion years ago, less than 400,000 years after the Big Bang, when the universe first became transparent. Before that, the universe was so hot and dense that light couldn't travel freely. It was a glowing fog, photons constantly scattering off free electrons. Then, as the universe expanded and cooled, electrons combined with nuclei to form neutral atoms. Light was free. That ancient light stretched by the expansion of the universe into microwaves still fills space. We call it the cosmic microwave background. It's the afterglow of creation, and it's everywhere. Your television tuned to static picks up a tiny fraction of it. About 1% of the static on an old analog TV is radiation from the birth of the universe. You're seeing the Big Bang, faintly, but it's there. Now think about lightning. A bolt of lightning is about 30,000 degrees Celsius, 5 times hotter than the surface of the sun. It's a plasma channel, a river of ions and electrons tearing through air, releasing energy at up to 1 billion volts. Why does lightning happen? Because clouds separate charges, ice crystals collide, electrons transfer positive charge, accumulates at the top of the cloud, negative at the bottom. The ground below becomes relatively positive. The voltage difference builds until the air itself breaks down, becomes conductive, and current flows. The bolt travels at about 1/3 the speed of light. The air around it heats so fast it explodes outward. That's thunder. Light moves faster, so you see the flash before you hear the sound. But here's something few people realize: lightning doesn't travel from cloud to ground in one stroke. It moves in steps. A faint tendril, called a stepped leader, descends in 50-meter jumps, ionizing the air as it goes. When it gets close enough to the ground, a streamer of positive charge rises up to meet it. They connect, and in that instant, a massive surge of current flows up the ionized channel, creating the bright flash you see. Most of the light comes from the return stroke moving upward. Lightning strikes up. Then there's the aurora, the northern and southern lights. Charged particles from the sun, electrons and protons stream toward Earth in the solar wind. Earth's magnetic field deflects most of them. But near the poles where the field lines converge, particles funnel down into the upper atmosphere. They collide with oxygen and nitrogen atoms. The collisions transfer energy. The atoms become excited electrons, jump to higher energy levels. Then they relax, falling back down, releasing the extra energy as light. Oxygen emits green and red. Nitrogen emits blue and purple. The colors dance across the sky, rippling curtains of light, a visible manifestation of electromagnetism shielding Earth from the sun's charged breath. Without that magnetic field, the solar wind would strip away our atmosphere over millions of years. Mars lost its magnetic field early in its history, and its atmosphere vanished. Earth kept its field, kept its air, kept its water, and life endured. Electromagnetism doesn't just build molecules, it protects worlds. Every photon you see, every shock you feel, every bond between atoms, every signal in your nerves, it's all electromagnetic. This is the force that fills space with light, that makes chemistry possible, that lets you see, touch, think. But deeper still, inside the nucleus of every atom, there's another force at work, far stronger, far stranger, operating at scales so small, the entire world of chemistry sits atop it, unaware. Inside every atom in your body, there's a war that should have been lost billions of years ago. Protons sit packed together in the nucleus, each one positively charged, each one repelling the others with electromagnetic force. They should fly apart instantly. The repulsion should tear atoms to pieces. But they don't scatter. Something holds them, something stronger than electromagnetism, something that operates in a space so small you could fit 1 trillion of them across the width of a human hair. This is the strong nuclear force, the most powerful force in nature. And without it, matter itself would not exist. Let's start with scale. The nucleus of an atom is about 10,000 times smaller than the atom itself. If an atom were a football stadium, the nucleus would be a marble at the center, and electrons would be grains of dust orbiting somewhere in the upper bleachers. But inside that marble, there's extraordinary violence being held in check. A proton is about 7 femtometers across. A femtometer is 10 to the power of -15 meters, a quadrillionth of a meter. At that scale, quantum mechanics rules and particles behave in ways that defy everyday intuition. Protons are made of smaller particles called quarks. Each proton contains 3 quarks, 2 up quarks, and 1 down quark, held together by the strong force. Neutrons also have 3 quarks, 1 up, 2 down. The force binding those quarks is mediated by particles called gluons. And gluons have a strange property: the farther apart you pull 2 quarks, the stronger the force between them becomes. It's the opposite of gravity or electromagnetism, where distance weakens the pull. With the strong force, distance strengthens it. Try to separate 2 quarks, and it's like stretching a rubber band. Pull harder, and the tension increases. Eventually, you put in so much energy that new quarks pop into existence from the vacuum, and you end up with 2 bound pairs instead of 2 free quarks. This is why we've never seen a lone quark. They're always confined inside protons, neutrons, or other particles. The strong force won't let them go. Scientists call this property confinement, and it's one of the strangest features of nature. Now here's what makes the strong force so powerful. It's about 100 times stronger than electromagnetism. At the scale of a nucleus, it overwhelms the electromagnetic repulsion between protons. That's why nuclei hold together. But the strong force has a catch. It only works over extremely short distances, roughly the size of a proton. Beyond about 1 to 3 femtometers, it drops to nearly 0. It's as if the force has a hard cutoff. Step outside its range, and it vanishes. This is why atoms don't stick together the way nuclei do. Once you're outside the nucleus, the strong force is irrelevant. Chemistry is governed by electromagnetism, which reaches much farther. But inside the nucleus, the strong force is everything. Consider carbon. A carbon nucleus has 6 protons and typically 6 neutrons. Those 6 protons, all positively charged, are crammed into a space about 5 femtometers across. The electromagnetic repulsion between them is enormous. Yet they stay bound because the strong force mediated by gluons holds them together. Add more protons, and the nucleus gets bigger. Eventually, you reach elements like uranium with 92 protons. The nucleus is stretched to its limit. Electromagnetic repulsion is nearly overpowering the strong force. Uranium is on the edge of stability. It decays slowly, but it decays. Go beyond uranium elements like plutonium americium, and the nuclei become even less stable. Some exist for only fractions of a second before falling apart. There's a limit to how many protons you can pack together before the strong force can no longer hold them. Scientists have created elements with over 100 protons in labs, but they decay almost instantly. The strong force is powerful, but it can only reach so far. Now let's talk about energy. Einstein's equation E equals mc squared tells us that mass and energy are interchangeable. A small amount of mass contains a staggering amount of energy. Nuclear binding energy is the energy required to pull a nucleus apart. It's also the energy released when a nucleus forms. And because the strong force is so powerful, that energy is immense. When 4 hydrogen nuclei fuse into one helium nucleus inside the Sun, the helium weighs slightly less than the 4 hydrogens combined. That missing mass, about 0.7%, is converted into energy. It doesn't sound like much, but the Sun converts about 4 million tons of mass into energy every single second. Not 4 million tons of fuel, 4 million tons of actual mass vanishing into light and heat and neutrinos. That's how powerful the strong force is. When you bind particles together with it, or break them apart, the energy released is millions of times greater than chemical reactions. This is why nuclear weapons are so devastating. The bombs dropped on Hiroshima and Nagasaki in 1945 each used about 64 kilograms of uranium or plutonium, but only a tiny fraction of that mass actually fissioned less than a kilogram. And of that, only about 700 milligrams converted into energy. 700 milligrams, less than the weight of a butterfly. That tiny conversion released the equivalent of 15,000 tons of TNT. The blast killed over 100,000 people instantly, and tens of thousands more in the following months. E equals mc squared. The speed of light squared is a very large number. Even a tiny amount of mass contains terrifying energy. This is the same process that powers the Sun, but in reverse. The Sun fuses light elements into heavier ones, releasing energy. Nuclear fission splits heavy elements into lighter ones, also releasing energy. Why does both fusion and fission release energy? Because of the shape of the nuclear binding energy curve. Iron 56 is the most stable nucleus. It has the highest binding energy per nucleon. Elements lighter than iron release energy when fused. Elements heavier than iron release energy when split. Iron sits at the bottom of the energy, while the most stable configuration. This is why stars can't fuse iron. Once a massive star's core turns to iron, fusion stops. There's no more energy to be gained. The core collapses, the outer layers explode, and the star dies in a supernova. And in that explosion, heavier elements are born. Gold, uranium, platinum forged in the fury of a dying star, scattered across space, eventually coalescing into planets, into oceans, into you. Every atom in your body, heavier than hydrogen, was made inside a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all built by nuclear fusion, powered by the strong force released in supernovae billions of years ago. You are made of stardust, not metaphorically, literally. The atoms that form you were forged in stellar cores and scattered by cosmic violence. But here's something most people don't realize: the strong force doesn't just bind quarks into protons and neutrons. It also has a residual effect that binds protons and neutrons into nuclei. Think of it this way. Quarks inside a proton are held by the strong force. But some of that force leaks out just a little and interacts with quarks in neighboring protons and neutrons. It's like magnetic attraction between atoms that are already internally bound by electromagnetism. This residual strong force is what holds the nucleus together. It's technically a side effect, a spillover from the deeper force binding quarks, but without it, nuclei would disintegrate. Atoms would never form chemistry, would never happen, and the universe would be a sea of unbound protons and electrons, cold and structureless, forever. Scientists didn't understand the strong force until the 20th century. Before then, atoms were thought to be indivisible. The word atom comes from the Greek atomos, meaning uncuttable. But in 1911, Ernest Rutherford discovered the nucleus. He fired alpha particles, helium nuclei, at a thin sheet of gold foil. Most passed through, but a few bounced back. Rutherford realized the atom was mostly empty space, with a dense, positively charged nucleus at the center. This created a problem. If the nucleus was packed with protons, why didn't it explode? Electromagnetic repulsion should tear it apart. Physicists proposed a new force, something strong enough to overpower electromagnetism at short range. They called it the strong nuclear force. But they didn't know what carried it. In 1935, Japanese physicist Hideki Yukawa predicted the existence of a particle that mediated the strong force. He calculated its mass should be about 200 times the mass of an electron. Scientists found particles in cosmic rays that seemed close, but it took until the 1960s and 70s to work out the full picture. Quarks and gluons, the deep structure of matter. Murray Gell-Mann and George Zweig independently proposed quarks in 1964. At first, many physicists thought quarks were just a mathematical trick, not real particles. But experiments in the late 60s at Stanford confirmed that protons and neutrons are made of smaller constituents. Gluons were harder to detect. They don't exist outside of particles, and they're never alone. But by the 1970s, evidence for them became undeniable. Quarks really are bound by gluons, and the strong force really does operate through their exchange. The theory describing this is called quantum chromodynamics, or QCD. It's one of the most successful theories in physics, but also one of the hardest to calculate with. The math is brutally complex. Supercomputers struggle to simulate what happens inside a single proton, but the predictions match experiments. QCD works. Now here's something strange. The strong force is so powerful, yet it's invisible to everyday life. You never feel it. It operates entirely within nuclei utterly confined, shaping matter from within, but never reaching out into the world you experience. Gravity shapes galaxies. Electromagnetism governs chemistry. Light touch. But the strong force, it sits silent at the heart of every atom, holding quarks together, keeping nuclei intact, enabling the existence of stable matter without ever making itself known directly. It's the hidden foundation, the unseen architecture, the force that makes forces possible, because without it, there would be no atoms, no molecules, no structures for other forces to act upon. And yet, even the strong force isn't the final word, because inside that same nucleus, another force is quietly at work, changing particles, transforming elements, letting the universe evolve from one state into another. Right now, as you breathe, particles inside your body are quietly betraying their identities. Neutrons are becoming protons. Protons, in rare cases, becoming neutrons. Particles transforming into other particles, releasing ghost-like neutrinos that pass through your body, through the earth, through everything barely interacting with anything at all. This is the weak nuclear force, the force of change, the force of decay, the reason atoms don't last forever, the reason the sun shines, the reason carbon-14 dating works, the reason you exist at all. Without the weak force, stars would never ignite, elements would never transform, the universe would be frozen in its primordial state, hydrogen-helium, and nothing else. No carbon, no oxygen, no complexity, no life. The weak force doesn't hold things together like the strong force. It doesn't reach across space like gravity or electromagnetism. It operates on the smallest scales at the shortest ranges, triggering transformations that ripple through time. It is the force that lets the universe evolve. Let's begin with the simplest example. A neutron alone, free outside an atomic nucleus. A free neutron is unstable. It doesn't last. On average, it survives about 15 minutes before it decays. Not hours, not years, minutes. When it decays, it transforms into a proton, an electron, and an antineutrino. This process is called beta decay, and it's mediated entirely by the weak force. Inside a nucleus, neutrons are often stable, held by the strong force, protected by the balance of particles around them. But free alone, they fall apart. The weak force whispers change, and the neutron obeys. This transformation is strange. A neutron isn't just rearranging its parts. One of its down quarks is actually changing into an up quark. Quarks can change flavor, up, down, strange, charm, bottom, top. The weak force allows this. The strong force doesn't. Electromagnetism doesn't. Only the weak force lets particles shift their fundamental identity. And when a quark changes, particles are born. The decay releases an electron, the particle we've known since the late 1800s. But it also releases something far stranger, an antineutrino. Neutrinos are ghost particles. They have almost no mass, so little that for decades scientists thought they might be massless. They have no electric charge, so electromagnetism ignores them. They don't interact through the strong force. The only forces they feel are gravity, which is negligible at particle scales, and the weak force. This makes them nearly invisible. A neutrino can pass through a light year of solid lead and probably not interact with a single atom. Right now, about 100 billion neutrinos from the sun are passing through your thumbnail every second. You don't feel them. They pass through your body, through the earth, out the other side, and continue into space. Only very rarely, maybe once in a trillion encounters, does a neutrino interact with matter. Scientists detect them using massive tanks of ultra-pure water buried deep underground, shielded from cosmic rays, waiting for that 1 in a trillion moment when a neutrino strikes a nucleus and produces a flash of light. It's like trying to catch shadows. But neutrinos are everywhere. They're produced in nuclear reactors, in supernovae, in the sun's core, in the decay of radioactive elements. They carry information from places light cannot escape, like the centers of stars or the hearts of collapsing neutron stars. In 1987, a star exploded in a nearby galaxy, the Large Magellanic Cloud, about 168,000 light-years away. The supernova, called SN 11987A, was the brightest seen from Earth in over 400 years. But here's the remarkable part. Neutrinos from that explosion reached Earth about 3 hours before the light did. How? Because neutrinos interact so weakly, they escaped the star's core immediately when it collapsed. Light, on the other hand, had to scatter through the dense outer layers, bouncing off atoms, taking hours to fight its way out. By the time the light emerged, the neutrinos were already long gone. Detectors in Japan and the United States recorded a burst of neutrinos on February 23, 1987. 3 hours later, telescopes saw the light. It was the first time in history that a cosmic event was detected through neutrinos before it was seen with light. Neutrinos gave us a glimpse of the supernova's core, the moment of collapse, the birth of a neutron star or black hole. Light only showed us the aftermath. This is the power of the weak force. It operates in realms where other forces cannot reach, triggering changes that ripple outward, shaping the universe in ways both subtle and profound. Now, let's talk about the sun. You've probably heard that the sun is powered by nuclear fusion. Hydrogen fuses into helium, releasing energy. But here's what most explanations skip. Fusion doesn't start with the strong force. It starts with the weak force. In the sun's core, temperatures reach about 15 million degrees Celsius. Protons' hydrogen nuclei slam into each other with tremendous energy. Normally, electromagnetic repulsion would push them apart. But at these speeds, at these energies, they sometimes get close enough for the strong force to bind them. Except, that's not quite right. 2 protons alone can't form a stable nucleus. They repel too strongly. What actually happens is stranger. 2 protons collide. In that instant, one of them transforms. The weak force changes one proton into a neutron, releasing a positron and a neutrino. Now, you have a proton and a neutron bound together. Deuterium, a stable isotope of hydrogen. This first step, this transformation, is the bottleneck. It's incredibly rare. A proton in the sun's core will on average wait about 10 billion years before successfully undergoing this fusion. 10 billion years of collisions, trillions upon trillions of failed attempts before one finally succeeds. But the sun has so many protons, about 10 to the 57th of them, that even with such a slow rate, fusion happens constantly. About 600 million tons of hydrogen fuse into helium every second. Without the weak force, that first step would never happen. Protons couldn't transform into neutrons. Fusion couldn't begin. The sun would be a cold, dark ball of hydrogen, and Earth would be a frozen rock orbiting a dead star. Every photon of sunlight that warms your skin, every ray that lets plants grow, every bit of energy that powers life on Earth, it all traces back to the weak force, allowing protons to change, allowing fusion to proceed, allowing stars to shine. Here's another application. One you might have heard of carbon dating. Carbon-14 is a radioactive isotope of carbon. It has 6 protons and 8 neutrons, making it unstable. Over time, it decays. One of its neutrons transforms into a proton, releasing an electron and an antineutrino. The atom becomes nitrogen-14. This decay happens at a predictable rate. Carbon-14's half-life is about 5,030 years. After that time, half of any sample will have decayed. After another 730 years, half of what remains decays. And so on. Living organisms constantly take in carbon from the atmosphere, including a small amount of carbon-14. When they die, they stop taking in new carbon. The carbon-14 they contain starts decaying, and the ratio of carbon-14 to stable carbon-12 decreases over time. By measuring that ratio, scientists can determine how long ago the organism died. This is how we date ancient wood-bone cloth, anything that was once alive. It's the weak force ticking like a clock, letting us read the age of the past. But the weak force is strange in other ways. It's called weak because it's weak, much weaker than electromagnetism or the strong force. Its range is even shorter than the strong force, operating at scales around 10 to the power of -18 meters, 1,000th the size of a proton. It's so weak and so short-ranged that for most of history, humans didn't even know it existed. Radioactivity was discovered in 1896 by Henri Becquerel, but it took decades to understand what was happening at the particle level. The weak force is mediated by particles called W and Z bosons. Unlike photons, which have no mass and travel at light speed, W and Z bosons are heavy about 80 to 90 times the mass of a proton. This is unusual. Force-carrying particles are generally massless or very light. The reason W and Z bosons are so heavy is tied to something called the Higgs field, but that's a story for later. What matters here is that their mass limits their range. A heavy particle can't travel far before it decays or disappears back into the vacuum. That's why the weak force operates at such short distances. Despite its weakness, the weak force has one unique power. It's the only force that violates something called parity symmetry. In physics, parity symmetry means that the mirror image of a process should behave the same as the original. Flip everything left to right, and the laws of physics shouldn't change. But the weak force doesn't respect this. It has a handedness. Neutrinos, for instance, only come in one variety left-handed. Antineutrinos are always right-handed. If you tried to create a right-handed neutrino, the weak force would refuse. It simply doesn't happen. This was discovered in 1956 by Chen-Xiong Wu, a Chinese-American physicist. She set up an experiment with cobalt-60, a radioactive isotope that decays via the weak force. She cooled the sample to near absolute zero and aligned the nuclei's spins using a magnetic field. Then, she watched which direction the emitted electrons went. If parity were conserved, electrons should be emitted equally in all directions, but they weren't. More electrons came out in one direction than the other. The weak force had a preference. Parity was violated. This was shocking. For decades, physicists assumed parity was a fundamental symmetry of nature. The weak force broke that assumption. And there's more. The weak force also plays a role in the matter-antimatter asymmetry of the universe. In the moments after the Big Bang energy condensed into particles matter and antimatter in equal amounts, electrons and positrons, protons and antiprotons, they should have annihilated each other completely, leaving nothing but light. But they didn't. a tiny imbalance existed. For every billion antimatter particles, there were 1,000,000,001 matter particles. When annihilation finished, that one extra particle per billion remained. We are that remainder. Everything you see, stars, planets, galaxies, is the residue of an ancient imbalance. Why the asymmetry scientists believe the weak force is part of the answer. It treats matter and antimatter slightly differently, violating something called CP symmetry. This tiny bias, compounded over the early universe's rapid expansion, could have tipped the scales. Without that bias, the universe would be empty. Pure light, no structure, no stars, no chemistry, no life. The weak force, in its strange asymmetric way, chose matter over antimatter. And here we are. Consider also how the weak force enables the periodic table. Elements heavier than hydrogen and helium, carbon, oxygen, iron, gold are all built inside stars through fusion. But some elements can only form through processes involving the weak force. Take neutron star mergers. When two neutron stars collide, they release torrents of neutrons. These neutrons are captured by atomic nuclei in rapid succession, building up heavy elements like gold, platinum, uranium. Many of these neutron-rich nuclei are unstable and decay via the weak force, transforming neutrons into protons, adjusting the element's identity. The gold in your ring, the iodine in your thyroid, the uranium that powers nuclear reactors, all forged in neutron star collisions sculpted by the weak force, as neutrons transformed into protons, shaping the periodic table one decay at a time. Without the weak force, the universe would be simpler. Hydrogen, helium, maybe lithium, but nothing else. No complexity, no chemistry, no pathways to life. The weak force is quiet, hidden, operating in shadows, at scales too small to see, on time scales too short or too long to notice directly. But its effects are everywhere. In the sunlight that reaches Earth, in the carbon dating of ancient bones, in the neutrinos streaming through your body, in the elements that build your cells. It is the force of transformation, the force of change, the force that says nothing stays the same. Everything decays into something new, and in that change, in that transformation, the universe finds a way to evolve, to build, to create. But these four forces, gravity, electromagnetism, strong, weak, they don't exist in isolation. They overlap, interact, emerge from deeper structures. Scientists have spent a century trying to understand how they fit together, how they unify, whether they're truly separate or just different faces of one underlying reality. Imagine holding a map of reality in your hands, not a map of countries or continents, but a map of everything that exists. Every particle, every force, every interaction that builds the universe from the ground up. A chart so complete that if you understand it, you understand why atoms hold together, why light travels, why stars burn, why you can think. That map exists. Scientists call it the standard model of particle physics, and it's one of the most successful theories ever written. But here's the strange part. It's incomplete. We know it's incomplete. There are blank spaces on the map, questions it can't answer, forces it can't explain. Yet, within its limits, it predicts the behavior of particles with absurd precision, accurate to 11 decimal places in some cases. It's a map drawn with exquisite detail, covering almost everything we can measure. But it doesn't cover everything that exists. The standard model organizes all known fundamental particles into categories. There are matter particles, quarks, and leptons. There are force-carrying particles, photons, gluons, W and Z bosons. And there's one special particle that gives others mass, the Higgs boson. 17 particles in total. That's it. Everything you see, touch, experience built from combinations of just 17 fundamental building blocks. Let's start with matter particles. Quarks come in 6 types or flavors: up, down, charm, strange, top, and bottom. Protons contain 2 up quarks and 1 down. Neutrons contain 1 up and 2 down. The other 4 flavors, charm, strange, top, bottom, only appear in high-energy collisions or cosmic rays. They're unstable and decay almost immediately. Then there are leptons. The most familiar is the electron orbiting atomic nuclei, carrying electric current enabling chemistry. But electrons have heavier cousins, the muon and the tau. They're like electrons, but with more mass. They decay quickly into lighter particles. Each of these charged leptons has a corresponding neutrino: electron, neutrino, muon, neutrino tau, neutrino. 3 flavors of ghost particles barely interacting with anything. 6 quarks, 6 leptons, 12 matter particles total. Now for every particle, there's an antiparticle. Same mass, opposite charge. Electron and positron. Proton and antiproton. When matter meets antimatter, they annihilate, converting entirely into energy. This symmetry, matter and antimatter, should mean the universe contains equal amounts of both. But it doesn't. The universe is overwhelmingly matter. Why, we don't fully know. Some asymmetry in the early universe possibly related to the weak force tipped the balance. That tiny imbalance is why you exist. Next, the force carriers. Photons carry the electromagnetic force. Their massless travel at light speed and mediate every interaction involving electric charge. Light itself is made of photons. So are radio waves, X-rays, microwaves. Gluons carry the strong force. There are 8 types of gluons, and they bind quarks together inside protons and neutrons. Gluons are strange because they interact with themselves. Photons don't interact with other photons, but gluons do, which is part of why the strong force behaves so oddly. W and Z bosons carry the weak force. Unlike photons and gluons, they're massive, about 80 to 90 times the mass of a proton. Their mass limits their range, which is why the weak force only operates at extremely short distances. Gravitons, in theory, would carry gravity, but we've never detected one. Gravity doesn't fit neatly into the standard model. It's the missing piece. Finally, there's the Higgs boson. In the 1960s, physicists realized the standard model had a problem. According to the equations, all particles should be massless. But clearly, electrons have mass. Protons have mass. W and Z bosons have mass. Something was wrong. Peter Higgs, along with several other physicists, proposed a solution: a field that permeates all of space, interacting with particles as they move through it. Particles that interact strongly with this field gain more mass. Particles that interact weakly gain less. Particles that don't interact at all, like photons, remain massless. This field came to be called the Higgs field, and its quantum excitation. The particle that represents it is the Higgs boson. But proposing a particle and finding it are very different things. The search for the Higgs boson took nearly 50 years. Scientists built larger and larger particle accelerators, smashing protons together at higher and higher energies, trying to create a Higgs boson in the debris of collisions. The Large Hadron Collider, or LHC, sits beneath the border of France and Switzerland. It's a ring 27 kilometers in circumference, buried 100 meters underground. Inside, protons are accelerated to 99.99991%, the speed of light, and smashed together. Each collision releases energy, and that energy can briefly condense into particles, sometimes particles that don't normally exist, like Higgs bosons. These particles decay almost instantly in less than a trillionth of a second. So scientists don't see the Higgs itself, they see its decay products and work backward to infer its presence. On July 4th, 2012, scientists at CERN announced they'd found it. A new particle mass about 125 times that of a proton, decaying in ways consistent with the Higgs boson. Peter Higgs, then 83 years old, was in the audience. He cried. He had predicted this particle in 1964. Nearly half a century later, it was real. The discovery confirmed the mechanism by which particles gain mass. It completed the Standard Model, and it earned Higgs and François Englert the Nobel Prize in Physics in 2013. But even with the Higgs, the Standard Model is incomplete. It doesn't include gravity. Einstein's general relativity describes gravity beautifully at large scales, but it's incompatible with quantum mechanics. We don't have a quantum theory of gravity. We don't know if gravitons exist. We can't unify gravity with the other forces. The Standard Model also doesn't explain dark matter, observations of galaxies. Galaxy clusters and the cosmic microwave background all point to the existence of matter that doesn't interact electromagnetically. It doesn't emit, absorb, or reflect light. It's invisible. We only detect it through gravity. About 85% of the matter in the universe is dark matter. None of the particles in the Standard Model fit the profile. Dark matter must be something else, something we haven't discovered yet. Then there's dark energy, which makes up about 68% of the universe's total energy. It's causing the universe's expansion to accelerate. We have no idea what it is. The Standard Model doesn't address it. So while the Standard Model describes ordinary matter beautifully, ordinary matter is only about 5% of the universe. The rest, 95%, is dark matter and dark energy, and we don't know what either one really is. There are other mysteries. Why are there 3 generations of particles? Electrons, muons, and taus are nearly identical, except for mass. Upcharm and top quarks follow the same pattern. Why 3? Why not 2, or 5, or just 1? Why do particles have the masses they do? The Higgs mechanism explains how particles get mass, but not why electrons are 0.511 million electron volts, while top quarks are 173,000 million electron volts. The masses seem arbitrary, yet they're incredibly specific. And why does the universe have the forces it does? Why 4 fundamental forces? Why not 1 or 10? These questions drive physicists to look beyond the Standard Model. Some propose supersymmetry or SUSY. The idea is that every particle has a heavier partner, a super partner, that we haven't detected yet, because it requires more energy to produce. Supersymmetry would solve several theoretical problems and could provide a candidate for dark matter. But so far, experiments haven't found any super partners. Others explore string theory, which suggests particles aren't points, but tiny vibrating strings. Different vibrations produce different particles. In string theory, gravity emerges naturally and all forces are unified. But string theory requires extra dimensions, not the 3 of space, and 1 of time we experience, but 10 or 11 total dimensions, most of them curled up so small we can't perceive them. String theory is mathematically beautiful, but it's also untested. We don't have experiments that can probe the scales where strings would reveal themselves. Another approach is loop quantum gravity, which proposes space-time itself is quantized, made of discrete units, like pixels on a screen. At the smallest scales, space and time aren't smooth. They're grainy. This could reconcile gravity with quantum mechanics without requiring extra dimensions. But again, it's unproven. The truth is, we don't know which path leads forward. Maybe supersymmetry, maybe strings, maybe something no one has thought of yet. What we do know is the Standard Model works. It predicts how particles behave with stunning accuracy. The magnetic moment of the electron, for instance, has been measured to agree with theory to 11 decimal places. 11. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. The Standard Model also explains forces through symmetries. Electromagnetism arises from a symmetry called U1. The weak force comes from SU2. The strong force from SU3. These aren't just mathematical tricks. They reflect deep structures in how the universe operates. In the 1960s and 70s, Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that electromagnetism and the weak force are actually two aspects of a single electroweak force. At high energies like those in the early universe, they're unified. As the universe cooled, the symmetry broke, and they split into two distinct forces. This was a huge breakthrough. For the first time, scientists showed that two seemingly different forces were actually one. They won the Nobel Prize in 1979. Since then, physicists have wondered, can we unify all the forces? Is there a grand unified theory or gut that merges electromagnetism, the weak force and the strong force, into one? Maybe. At energies around 10 to the 16th billion electron volts, far beyond what any accelerator can reach, some theories predict the three forces converge to equal strength. If we could probe that energy, we might see them unify, but we can't. That energy scale corresponds to particles with masses trillions of times heavier than anything we can produce. We'd need an accelerator the size of the solar system. So instead, we look for indirect evidence. Proton decay, for instance. Some grand unified theories predict protons should eventually decay into lighter particles. The half-life would be absurdly long, 10 to the 34th years or more, but with enough protons, you might see one decay. Experiments have been running for decades, watching tanks of ultra-pure water waiting to catch a proton in the act of disintegrating. So far, nothing. Protons appear to be stable, or at least far more stable than guts predict. Maybe grand unified theories are wrong, or maybe proton decay is even rarer than we thought. And then there's gravity. Even if we unify the three quantum forces, gravity still stands apart. To include it, we'd need a theory of everything, a single framework that describes all four forces, all particles, all interactions, from the smallest scales to the largest. Einstein spent the last 30 years of his life searching for such a theory. He failed. Decades later, we're still searching. But here's what's beautiful. Even without the final answer, even with blank spaces on the map, the Standard Model reveals an extraordinary structure. 17 particles arranged in patterns interacting through forces that emerge from symmetries governed by equations that predict reality with astonishing precision. It's a glimpse of the underlying order, a hint that the universe, for all its complexity, follows rules. Deep, elegant, mathematical rules. We've decoded part of the language the cosmos speaks. Not all of it, but enough to see that reality has grammar syntax structure. Enough to wonder what the full sentence might say. These forces, these particles, they're not just abstractions. They're active right now, in your body, in the air, in the light, streaming past. Every breath, every thought, every moment of existence is the standard model in motion. What if everything is one thing? 4 forces govern the universe. But maybe at the deepest level, they're not really separate. Maybe they're different expressions of a single unified force, a force we haven't fully understood yet, but one that underlies all of reality. This idea has haunted physicists for over a century. The dream of unification. The search for a theory that shows how gravity, electromagnetism, and the nuclear forces emerge from one elegant structure. One equation. One truth. Einstein spent the last 30 years of his life chasing this dream. He died without finding it. But the search continues, and in some ways, we've come closer than he ever imagined. In 1687, Isaac Newton unified celestial and terrestrial motion. Before him, people thought the heavens obeyed different laws than Earth. Planets moved in perfect circles because they were divine. Objects on Earth fell because they sought their natural place. Newton said no. The same force that pulls an apple to the ground holds the moon in orbit around Earth, around the sun and stars in their galaxies. One law. Universal gravitation. It was the first great unification in physics, and it changed everything. In the 1860s, James Clerk Maxwell achieved the second unification. He showed that electricity and magnetism weren't separate phenomena. They were 2 aspects of one force, electromagnetism. His equations predicted electromagnetic waves which turned out to be light. One force governing electric charge, magnetic fields, and the entire spectrum of radiation. 2 forces unified. 2 mysteries solved. Physicists began to wonder, could we unify everything? By the early 20th century, there were 2 great theories. General relativity, which described gravity as the curvature of space-time, and quantum mechanics, which described the behavior of particles and fields at the smallest scales. Both theories worked brilliantly within their domains, but they contradicted each other. Relativity was smooth, continuous, deterministic. Quantum mechanics was grainy, probabilistic, strange. Einstein believed there had to be a deeper layer, a theory that unified them. He called it the unified field theory. He tried for decades to merge gravity and electromagnetism into one framework. He failed. The math didn't work. The predictions didn't match experiments. He died in 1955, still searching. But in the decades after his death, other physicists succeeded, where Einstein could not by unifying gravity, but by unifying the other forces. In the 1960s, 3 physicists, Sheldon Glashow, Abdus Salam, and Steven Weinberg, developed the electroweak theory. They showed that electromagnetism and the weak nuclear force were not separate. At high energies, they merged into one force. Here's how it works in the moments after the Big Bang. The universe was incredibly hot and dense. Energy was so high that the electromagnetic and weak forces were indistinguishable. There was just one electroweak force. As the universe expanded and cooled, a phase transition occurred. The Higgs field, which had been symmetric, acquired a value everywhere in space. This broke the symmetry, splitting the electroweak force into 2 distinct forces: electromagnetism carried by massless photons, and the weak force carried by massive W and Z bosons. It's like water freezing into ice. At high temperatures, water is liquid and symmetric in all directions. At low temperatures, it crystallizes, breaking symmetry and forming rigid structures. The universe underwent something similar. Glashow, Salam, and Weinberg predicted specific particles and interactions. When experiments at CERN confirmed the W and Z bosons in 1983, the electroweak theory was validated. The three scientists won the Nobel Prize in 1979, even before the experimental proof. This was monumental. For the first time, scientists showed that two of the four fundamental forces were actually one. So now there were three forces: gravity, electroweak, and strong. Could we unify further? Physicists developed grand unified theories, or GUTS, attempting to merge the electroweak and strong forces. The idea is that at even higher energies, around 10 to the power of 15 or 16 billion electron volts, the three non-gravitational forces would converge into a single force. Some GUT models predict that protons should decay, albeit with extraordinarily long half-lives, something like 10 to the power of 34 years. That's a trillion times the current age of the universe. But with enough protons, statistics say, you might catch one decaying. Experiments like Super Kamio Kande in Japan have monitored tanks containing thousands of tons of ultra-pure water for decades, watching for a single proton to disintegrate. So far, nothing. Either protons are even more stable than predicted, or the simplest GUTS are wrong. Still, the mathematical structure of GUTS is compelling. The idea that forces unify at high energy isn't just speculation. We've seen it happen with electromagnetism and the weak force. Why not the strong force, too? But gravity remains the outlier. No matter how physicists try, they can't fit gravity into the quantum framework. General relativity describes gravity as geometry, the curvature of space-time. Quantum mechanics describes forces through particle exchanges and probabilistic fields. The two languages don't translate. At everyday scales, this isn't a problem. Gravity governs planets and stars. Quantum mechanics governs atoms and particles. They operate in different arenas, but there are places where both should matter: the centers of black holes, where gravity becomes infinitely strong in an infinitely small space. The first moments after the Big Bang, when the entire universe was compressed to quantum scales. In these regimes, you need a theory that merges quantum mechanics and general relativity. We don't have one. When you try to calculate quantum gravity using standard methods, the equations blow up. You get infinities that can't be removed. The math breaks. Something is fundamentally wrong or fundamentally missing. String theory is one attempt to solve this. Instead of treating particles as point-like objects, string theory proposes their tiny, one-dimensional loops or strands. Different vibrational patterns of these strings produce different particles. An electron is one vibration, a quark, another, a photon, another. In string theory, gravity emerges naturally. One particular vibration of a string corresponds to the graviton, the hypothetical particle that carries gravity. General relativity isn't something you add. It's something you derive from the deeper string framework. String theory also unifies all the forces. Electromagnetism, weak, strong, and gravity all arise from the same underlying strings, just vibrating in different ways. It sounds beautiful, but there's a catch. String theory requires extra dimensions, not just the 3 spatial dimensions and 1 time dimension we experience, but 10 or 11 total dimensions. Most of these extra dimensions are curled up so tightly at scales around the Planck length 10 to the power of minus 35 meters that we can't detect them. Why would the universe have hidden dimensions? In string theory, it's necessary for the math to work. Strings need space to vibrate in complex ways. If you constrain them to just 3 dimensions, the theory falls apart. But we can't test this. We can't probe scales that small. And string theory makes very few predictions that we can verify with current experiments. Some critics say it's not even science, it's mathematics, masquerading as physics. Proponents argue that string theory is still developing. Maybe one day it will make testable predictions. Maybe we'll find indirect evidence for extra dimensions or supersymmetric particles, but for now, it remains a framework without experimental support. Another approach is loop quantum gravity. Instead of treating space-time as smooth, this theory proposes it's made of discrete units, tiny loops of space quantized and granular like pixels on a screen. At the Planck scale, space-time wouldn't be continuous. It would be a network of interconnected loops, a kind of fabric woven from quantum threads. Gravity would emerge from the collective behavior of these loops. Loop quantum gravity doesn't require extra dimensions. It works in the familiar 4 dimensions of space-time, and it might resolve singularities, places where general relativity predicts infinite density, like black hole centers or the Big Bang. In loop quantum gravity, singularities might be replaced by quantum bounces or bridges. But loop quantum gravity has its own challenges. It's difficult to connect it to the standard model. And like string theory, it's hard to test. The scales it describes are far beyond our experimental reach. So we have 2 major candidates, string theory and loop quantum gravity, both mathematically intriguing, both untested. And there may be other approaches we haven't thought of yet. What's clear is that unifying gravity with quantum mechanics is hard, really hard. It's been nearly a century since quantum mechanics was formulated, and we still don't have a working quantum theory of gravity. Why is gravity so different? One reason might be its weakness. Gravity is 10 to the power of 36 times weaker than electromagnetism. At particle scales, it's negligible. We only notice gravity when vast amounts of mass accumulate, planets, stars, galaxies. Maybe the rules governing gravity are fundamentally different, because gravity operates in realms the other forces don't. Or maybe we're thinking about it wrong. Some physicists propose that gravity isn't a fundamental force at all, but an emergent phenomenon, something that arises from deeper quantum processes, the way temperature emerges from molecular motion. If gravity is emergent, then trying to quantize it, like the other forces, is misguided. We need to understand what it emerges from first. These are open questions, active research. We're still feeling our way forward in the dark. But here's what we do know. Unification has happened before. Maxwell unified electricity and magnetism. Glashow, Salam, and Weinberg unified electromagnetism and the weak force. Each unification revealed that what seemed like separate forces were actually facets of something deeper. It's reasonable to think the pattern continues. Maybe the strong force joins the electro-weak at higher energies. Maybe all 4 forces, including gravity, converge into one at the Planck scale. If that's true, then in the first moments after the Big Bang, in the first 10 to the power of minus 43 seconds, before the universe was even a trillionth of a trillionth of a trillionth of a second old, there was only one force, one unified field governing everything. Then, as the universe expanded and cooled, symmetries broke. The unified force split. First gravity separated, then the strong force. Then, at lower energies, the electroweak split into electromagnetism and the weak force. 4 forces emerged from one. The universe diversified, complexified, built structure from simplicity. If we could rewind time or achieve the energies of the early universe, we'd see the forces merge back into one. We'd witness the universe in its most symmetric, unified state. But we can't. Those energies are inaccessible. The best we can do is build bigger accelerators, smash particles at higher speeds, and look for hints, anomalies, unexpected particles, signs of deeper structure. The Large Hadron Collider probes energies around 14 trillion electron volts. That sounds like a lot, but it's nothing compared to the Planck energy, which is around 10 to the power of 28 electron volts. To reach that, we'd need an accelerator the size of the Milky Way galaxy. We're not going to build that. So instead, we look for indirect evidence. We study the cosmic microwave background, searching for imprints of quantum gravity in the earliest moments. We observe black holes, hoping to catch phenomena that reveal quantum effects in strong gravity. We measure the properties of particles with absurd precision, looking for tiny deviations that might hint at new physics. We search, we calculate, we wonder. And we remember that science is a process, not a destination. Newton didn't have the final theory of gravity. Einstein refined it. Einstein didn't have a theory of quantum gravity. Someone, someday will. The search for unification isn't just about elegance, it's about understanding. If the 4 forces are truly one, then the universe has a single coherent explanation. A theory of everything. One set of principles that governs atoms, stars, galaxies, and the fabric of space-time itself. That would be profound, not just because it completes the map, but because it reveals the universe as a unified whole, not a collection of separate rules, but a single, interconnected reality. Einstein believed this. He spent his final decades in pursuit of it. He didn't succeed, but his effort shaped the course of physics. Every search for unification since has stood on his shoulders. Maybe we'll find the answer in our lifetime. Maybe it will take centuries. Maybe the universe will surprise us with something we never expected. But the question remains, and the search continues. 4 forces. One universe. One truth waiting to be discovered. Yet, while physicists chase unification in equations and experiments, these same forces are at work everywhere, every moment, not just in particle colliders, but in your body, in the air, in the sunlight. These abstract forces have practical, tangible, beautiful consequences. You woke up this morning because of forces you'll never see. Sunlight streamed through your window electromagnetic radiation that traveled 150 million kilometers in 8 minutes, carrying energy from nuclear fusion powered by the strong and weak forces. That light struck your retina, triggering chemical reactions held together by electromagnetic bonds, sending electrical signals through neurons to your brain, where they became the experience of seeing. You stood up. Gravity pulled you down. Electromagnetic forces in your muscles contracted, lifting you against that pull. Your feet pressed against the floor, and electromagnetic repulsion between the atoms in your skin and the atoms in the ground created the sensation of solid contact, even though the atoms never actually touched. Every single moment of your life is physics in motion. Forces you learned about, in abstract terms, they're not abstract. They're here. They're you. Let's start with something simple. Walking. When you walk, you're negotiating a delicate balance between gravity and friction. Gravity pulls you toward the center of the earth with a force equal to your mass times 9.8 meters per second squared. That's your weight, the downward pull you feel constantly. But you don't sink into the ground because the ground pushes back with an equal force. This is electromagnetic repulsion. Electrons in your shoes repel electrons in the floor. The resistance feels solid, immovable, but it's really just electric fields shoving against each other. Friction lets you move forward. When you push your foot backward, friction also, electromagnetic caused by molecular interactions between surfaces, pushes you forward. Without friction, you'd slip like walking on ice. Ice is slippery because pressure and friction briefly melt the top layer, creating a thin film of water that reduces molecular grip. Less friction, less control. Your foot slides. On rough surfaces, microscopic bumps and valleys interlock. More friction, more grip. Same force, different texture. Every step you take is a negotiation between gravity pulling you down, electromagnetic forces holding you up, and friction letting you move forward. Three forces coordinated unconsciously millions of times throughout your life. Now let's talk about breathing. Right now, air is flowing into your lungs. You probably don't think about it, but it's happening because of pressure differences created by molecular collisions. Air is mostly nitrogen and oxygen molecules moving at hundreds of meters per second, bouncing off each other and off surfaces. When they hit the walls of your lungs, they exert pressure. When your diaphragm contracts, your chest cavity expands. The volume increases, pressure drops, and air rushes in from outside where the pressure is higher. This is gas law in action. Pressure volume and temperature are linked. Increase the volume, decrease the pressure. Molecules spread out, collide less often with the walls. Air flows from high to low pressure, always seeking equilibrium. Each breath brings in about 500 milliliters of air, roughly half a liter. That air contains about 10 to the power of 22 molecules. 10 billion trillion molecules entering your lungs, diffusing through membranes, binding to hemoglobin in your blood, traveling to cells throughout your body. Hemoglobin is a protein. Its shape is determined by electromagnetic forces, hydrogen bonds, ionic interactions, hydrophobic effects. Oxygen binds to iron atoms in hemoglobin, held there by electromagnetic attraction, carried through blood vessels, released in tissues where it's needed. All chemistry. All electromagnetic force. Now think about your heart. Right now, as you rest, it's beating, probably around 60 to 80 times per minute. Each beat pumps about 70 milliliters of blood. Over the course of a day, your heart moves about 7,000 liters of blood through your body. Over a lifetime, that's hundreds of millions of liters. What makes it beat electricity? Your heart has its own pacemaker cells located in the sinoatrial node. These cells spontaneously generate electrical signals. Sodium and potassium ions, charged particles, flow through channels in the cell membrane. When enough positive ions enter the cell, reaches a threshold, and fires, sending an electrical impulse through the heart muscle. The impulse spreads in a wave. Muscle cells contract in sequence, squeezing blood from the atria into the ventricles, then out into the arteries. The whole process takes less than a second, and it happens automatically, continuously, from before you're born until the moment you die. It's electromagnetism coordinated across billions of cells, keeping you alive. Your brain is even more electric. About 86 billion neurons, each connected to thousands of others, forming a network of trillions of synapses. When a neuron fires, it sends an electrical signal down its axon, a long, thin fiber that can stretch from your spinal cord to your toes. The signal travels at speeds between 1 and 120 meters per second, depending on the type of neuron. Some are insulated with myelin, a fatty sheath that speeds transmission. Others are bare, slower, but still fast enough to coordinate movement, sensation, thought. At the synapse, the gap between neurons, the electrical signal triggers the release of neurotransmitters. These are molecules: dopamine, serotonin, glutamate, GABA. They drift across the gap, bind to receptors on the next neuron, and trigger a new electrical signal. This is how you think. Patterns of electrical activity cascading through networks modulated by chemistry. Every memory you have, every emotion you feel, every decision you make, it's neurons firing ions, flowing electromagnetic forces, shaping the structure of your mind. Even your DNA relies on electromagnetic forces. The double helix is held together by hydrogen bonds between base pairs. Adenine pairs with thymine, guanine with cytosine. These pairings are specific because of the shape of the molecules and the electromagnetic attraction between them. Hydrogen bonds are weak individually, about 20 times weaker than covalent bonds. But there are billions of them along the length of a DNA molecule. Together, they're strong enough to keep the helix stable, yet weak enough to unzip when enzymes need to read or copy the genetic code. When your cells divide, enzymes pull the two strands apart. New nucleotides float in and pair up with the exposed bases, forming two identical copies. The process is guided entirely by electromagnetic forces, the shapes of molecules, the attraction between charges, the repulsion that keeps incorrect pairings from forming. Life itself is chemistry, and chemistry is electromagnetism, arranging atoms into patterns complex enough to replicate, metabolize, evolve. Now let's step outside your body and look at your phone. Touchscreens work through capacitance. The screen is coated with a material that stores electric charge. Your finger, being conductive, disrupts the electric field when it gets close. Sensors detect the change and calculate where you touched. You're not actually touching the screen. Remember, there's still a gap, but the electromagnetic field of your finger interacts with the field of the screen, and that interaction is detected, interpreted, turned into a command. Every swipe, every tap, it's electromagnetic force sensed and processed in milliseconds. Inside the phone, electricity flows through circuits at nearly the speed of light. Electrons move through silicon pathways, switching transistors on and off billions of times per second. Each transistor is a tiny gate controlled by voltage. Open, current flows. Closed, it stops. Billions of these gates working together perform calculations. They run algorithms, render graphics, connect to wireless signals. The phone in your hand contains more computing power than the entire Apollo program that sent humans to the moon. All of it powered by electromagnetism. Even the light from your screen is electromagnetic radiation. LEDs, light-emitting diodes, convert electrical energy into photons. Electrons jump from a higher energy level to a lower one, releasing the energy difference as light. Red, green, blue. Millions of tiny pixels, each one glowing at different intensities, combining to form images, text videos. You're looking at controlled electromagnetic radiation, carefully tuned to simulate reality. Now think about the sun. Every morning, sunlight falls on your skin. Photons born in the sun's core through nuclear fusion take about 100,000 years to random walk their way to the surface, bouncing off atoms, gradually drifting outward. Once they escape, they travel through space at light speed, reaching Earth in 8 minutes. When a photon strikes your skin, it's absorbed by molecules. The energy is converted into heat, molecular vibrations. You feel warmth. That warmth came from the sun's core, where 4 hydrogen nuclei fused into one helium nucleus, mediated by the weak force bound by the strong force released as gamma rays that eventually became the visible and infrared light warming your face. Fusion, transformation, radiation, all forces working in sequence. Or think about Earth's magnetic field. It's generated by electric currents in the molten iron core about 3,000 kilometers below your feet. As the core rotates and convects, it creates moving charges, which produce magnetic fields. This is called the geodynamo. The field extends thousands of kilometers into space, forming the magnetosphere. It deflects most of the charged particles streaming from the sun in the solar wind. Without it, those particles would strip away the atmosphere over millions of years, the way they did on Mars, after its magnetic field collapsed, the aurora borealis. The northern lights happens when some charged particles follow magnetic field lines down toward the poles colliding with oxygen and nitrogen in the upper atmosphere. The collisions excite the atoms, and when they relax, they emit light. Green from oxygen, red from high-altitude oxygen, blue and purple from nitrogen. It's the electromagnetic force protecting Earth painting the sky. Even taste and smell are electromagnetic. When you eat, molecules from food bind to receptors on your tongue and in your nose. The binding is specific. Certain shapes fit certain receptors, like keys in locks. The fit is determined by electromagnetic interactions, the distribution of charge, the shape of electron clouds, the hydrogen bonds that form between molecule and receptor. When a molecule binds, it changes the shape of the receptor protein. That change triggers a signal, an electrical impulse sent to your brain, where it's interpreted as taste or smell, sweetness, saltiness, bitterness, sourness, umami, all electromagnetic interactions translated into sensation. The same for touch. Pressure receptors in your skin detect mechanical deformation. When something presses against your skin, receptors compress opening ion channels, allowing charged particles to flow, generating an electrical signal. Hot and cold are detected by different receptors sensitive to temperature changes. Pain receptors respond to tissue damage, extreme temperatures, or chemical signals released by injured cells. All of these signals travel as electrical impulses to your brain, where they're assembled into the experience of feeling. You don't just live in a world governed by forces. You are forces interacting constantly with everything around you. Your body is a symphony of electromagnetic coordination, held together by quantum bonds, powered by nuclear energy, from a star existing, because gravity gathered dust into a planet and kept it stable for billions of years. Every breath is molecular collision. Every thought is electric fire. Every heartbeat is timed by ion flow. Every step is friction against electromagnetic repulsion. Every sight is photons translated into neural code. Forces aren't distant abstractions. They're immediate. They're intimate. They're the reason you exist and the mechanism by which you experience existence. But these forces, for all their power and precision, also raise a deeper question. Not just how they work, but why they're here at all. Why does the universe have these forces? Why are they balanced so perfectly? Why does anything exist instead of nothing? There's a question that keeps physicists awake at night, a question so simple a child could ask it, yet so profound that no one has ever answered it satisfactorily. Why is there something instead of nothing? Why does the universe exist? Why does it have these four forces arranged just so balanced, to one part, in 10, to the power of 60? Why atoms? Why stars? Why galaxies? Why you? The honest answer is, we don't know. But the search for that answer has revealed something extraordinary. The universe isn't random. It's structured. It follows rules. Deep mathematical, elegant rules that we've slowly, painstakingly decoded over centuries. Four forces hold everything together. Gravity bending space and time itself, shaping the cosmos at the largest scales. Electromagnetism, lighting up the world, binding atoms into molecules, letting chemistry happen, letting you see and touch and feel the strong nuclear force hidden inside every atom, gripping quarks together, making matter stable enough to exist, and the weak nuclear force, quiet and strange, allowing particles to transform stars to shine elements to evolve. Four forces. That's all. And somehow, from just these four, the entire universe emerges. Galaxies spiral, stars fuse hydrogen into heavier elements, planets form, life begins, consciousness arises, and here you are, listening to these words, wondering how it all fits together. Scientists have measured the strength of these forces with absurd precision. Gravity is the weakest, about 10 to the 36th power, times weaker than electromagnetism. If it were even slightly stronger, stars would burn out in millions of years instead of billions. Life wouldn't have time to evolve. If electromagnetism were slightly weaker, atoms wouldn't bond into molecules. Water wouldn't exist. DNA couldn't form. Chemistry as we know it would be impossible. If the strong force were just 5% weaker deuterium, the first step in stellar fusion couldn't form. Stars wouldn't shine. The universe would be cold dark, filled with nothing but hydrogen and helium. If the weak force didn't exist, fusion in stars would proceed differently. The sun might not burn at all. Or it might burn too fast, exhausting its fuel before planets had time to cool and stabilize. These aren't wild speculations. These are calculations. Scientists have modeled what the universe would look like if the forces had slightly different strengths, and in nearly every variation, the universe becomes sterile. No stars, no planets, no atoms complex enough to build life. We live in a universe balanced on a knife's edge. Some call this the fine-tuning problem. The constants of nature, the strength of forces, the masses of particles, the rate of cosmic expansion, all seem precisely calibrated to allow complexity structure life. Why one answer is the anthropic principle. The universe must be capable of supporting observers because otherwise there would be no one here to observe it. We exist, therefore. The universe must allow existence. It's a selection effect. We don't live in the universes where life is impossible, because in those universes, there's no one to ask the question. But this doesn't explain why our universe has the properties it does. It just says, if it didn't, we wouldn't be here to wonder. Some physicists propose a multiverse, an infinite number of universes, each with different physical laws, different constants, different forces. Most are sterile, empty, lifeless. But somewhere in a tiny fraction of them the constants align, just right, and stars form. Planets coalesce, chemistry happens, and life emerges. We live in one of those rare universes, not because it was designed for us, but because those are the only universes where beings like us can exist to observe. It's a compelling idea, but it's also untestable. If other universes exist, we can't reach them, can't detect them, can't observe them. They're beyond the scope of science, at least for now. Another possibility is that there's a deeper theory we haven't discovered yet, one that explains why the constants have the values they do. Maybe the universe couldn't be any other way. Maybe the laws of physics, once fully understood, will reveal that these four forces, with these specific strengths, are the only logically consistent configuration. Maybe the universe is the way it is, because it has to be, or maybe not. Maybe we'll never know. Maybe the question of why is beyond the reach of science, forever locked behind the horizon of what we can measure, test, and prove. But here's what we do know. The universe exists, and it's comprehensible. We've decoded much of its language. We've mapped its particles, measured its forces, traced its history back to the first fraction of a second after the Big Bang. We know the universe is 13.8 billion years old. We know it's expanding, and that expansion is accelerating, driven by something we call dark energy, a force or field that makes up 68% of the universe's total energy. Yet we don't understand what it is. We know that about 27% of the universe is dark matter, invisible, detectable only through gravity holding galaxies together in ways visible matter alone cannot. That means everything we can see, stars, planets, galaxies, nebulae, everything made of atoms, accounts for only about 5% of the universe. 5%. The other 95% is dark, unknown, waiting to be understood. This is humbling. We've learned so much, yet the universe is still mostly mystery. The forces we've discussed tonight govern that 5%. The ordinary matter, the stuff we interact with, study, build our lives upon. But beyond that, there's an entire cosmos of phenomena we barely glimpse. Dark matter, dark energy, quantum gravity, the unification of forces. These are the frontiers, the blank spaces on the map. And maybe that's how it should be. Science isn't about having all the answers. It's about asking better questions. Every discovery reveals new mysteries. Every answer opens new doors. Newton discovered universal gravitation, but couldn't explain what gravity was. Einstein explained it as space-time curvature, but couldn't reconcile it with quantum mechanics. We've unified electromagnetism and the weak force, but not the others. We've found the Higgs boson, but not dark matter particles. Each generation advances a little further. The map grows. The mystery deepens. And in that deepening mystery, there's wonder. Think about this. You are made of atoms forged in the hearts of stars, the calcium in your bones, the iron in your blood, the oxygen you breathe, all created in nuclear furnaces billions of years ago, scattered across space when those stars exploded, gathered by gravity into new clouds, condensed into planets incorporated into living cells. You are stardust assembled into a form that can wonder about stars. Every atom in your body has been part of countless other structures. The carbon in your DNA was once part of a blade of grass, an ancient tree, a dinosaur, a sea creature, a microbe in primordial oceans. Atoms cycle. They're reused, recycled, reformed. You're not separate from the universe. You're a temporary pattern, a configuration of atoms held together by forces animated by chemistry, aware of itself for a brief flicker of time. And in that flicker, you can understand. You can ask why. You can trace the history of forces back to the beginning, forward to the end, inward to the quantum scale, outward to the cosmic horizon. You can know that gravity bends space-time, that light is an electromagnetic wave, that quarks are bound by gluons, that neutrinos pass through your body unfelt. You can marvel at the fact that 4 forces, just 4, are enough to build everything. Stars and planets, DNA and neurons, thought and wonder, and the capacity to ask why we don't have the final answer. Maybe we never will. But the search itself is beautiful. The effort to understand, to map the invisible architecture of reality, to decode the language the cosmos speaks, that effort is what makes us human. Tonight, we've walked through the forces that hold the universe together. We've seen how they work, where they come from, what they do. We've traced them from the smallest scales to the largest, from the quantum foam to the structure of galaxies. We've learned that gravity, though weak, reaches infinitely far and shapes everything. That electromagnetism binds atoms, carries light, lets you see and touch and think. That the strong force grips quarks into protons, holds nuclei together, powers stars. That the weak force transforms particles, allows decay, lets the universe evolve. And we've seen that these forces aren't distant abstractions. They're here now, in every breath, every heartbeat, every thought. You're held together by them. You exist because of them. The cosmos holds together, and so do you. Not by accident, but by forces so perfectly balanced they let stars burn for billions of years, atoms bond into molecules. Chemistry give rise to life, and life give rise to minds that can look up at the night sky and wonder why. We've come far in our understanding, from Newton's apple to Einstein's curved space-time, from Maxwell's equations to the Standard Model, from the discovery of radioactivity to the detection of gravitational waves. But the journey isn't over. The map still has blank spaces, dark matter, dark energy, quantum gravity. The unification of forces, these mysteries remain, and new mysteries will emerge as we probe deeper. Perhaps one day someone will find the theory of everything, the single equation that describes all forces, all particles, all interactions. Perhaps we'll understand why the universe exists, why the constants have the values they do, why something instead of nothing. Or perhaps the mystery will always remain just beyond reach, reminding us that the universe is larger, stranger, and more wonderful than we can fully grasp. Either way, the search continues, and you're part of it. By wondering, by asking, by trying to understand, you participate in the greatest adventure humanity has ever undertaken, the quest to comprehend the cosmos. four forces, infinite manifestations, one universe holding itself together through gravity, electromagnetism, and the nuclear forces, one reality woven from fields and particles, energy and space-time following rules we've only begun to decode. And somewhere in that vast unfolding mystery, you exist. A pattern of atoms held by forces aware of forces, wondering about forces. Held together, held here, held for now. Sleep well, dream gently. And when you wake, remember you are stardust held together by invisible threads, part of a universe that somehow impossibly beautifully exists. Thank you for joining me on this quiet journey through the forces that shape everything. I hope these whispered truths about gravity, light, and the hidden architecture of atoms brought you comfort, curiosity, and maybe a little wonder. If you'd like more stories, told softly, more science, whispered into the dark, stay close. There are more mysteries, waiting black holes, and time quantum strangeness, and the edge of the knowable, the birth of stars, and the fate of galaxies. Until then, rest easy. The forces that hold the cosmos together are holding you too. Good night.